great pleasure to introduce our GPCE keynote speaker, Saman Amarasinghe from Massachusetts Institute of Technology, MIT, here in Boston. So Saman is one of the pioneers and leaders of performance-oriented DSLs, right? So I think most people in this room will at least have heard about StreamIt and Halide and Petabricks and also perhaps OpenTuner, which is one of the works that has led the way of using machine learning techniques for compiler optimizations, right? And all of Saman's work really combines both language design coupled with compiler optimization techniques to really push the boundary in terms of performance, what you can get out of current and emerging hardware architectures. So in today's talk, Saman will speak about some of his most recent work on TACO, which is about sparse tensor algebra. And I should say that we're really lucky to have him here today because he's not only an accomplished professor and researcher, but he's also taking a leadership role at MIT as associate department head. So welcome, Saman.
Thank you. So when I announced this talk in my abstract, I said I'm going to talk about both tensor algebra compiler and on GraphIt graph language. Except I realized I have too much stuff to talk about tensors, so and I'm not going to talk about GraphIt. So if you're here to know what GraphIt, I'm sorry. So I'm going to spend most of the time on TACO, our tensor algebra compiler. This is joint work with a bunch of people. Some of them are in this room. Fred is here. Okay, yeah. Okay, so if you look around, tensors are everywhere. So if you look at data analytics, the data can be represented as tensors. And if you look at machine learning, a lot of machine learning data is represented as tensors. And before any of these things like data analytics and machine learning came in the scene, scientific and engineering computation for a very long time, the data was represented as tensors. So I am very confident to say that because I basically say everything is a tensor. Scale is a zero-dimension tensor, vector is a one-dimensional tensor, and matrix is a two-dimensional tensor. So in that sense, everything is a tensor. So every time you write a program, it's basically a tensor. But normally people refer to things as tensors if it is more than 2 dimensions. So let's look at one of these interesting tensors, which is this Amazon product reviews. So this data is basically every time you buy a product and write a review, you get this data. So it can be viewed as this 3-dimensional matrix in here, tensor here. So one dimension is all the products, other dimension is all the users, and other dimension is the words they use to write this review. So this can be used for a lot of things like recommendation, sentiment, all these things can be calculated using this tensor. However, if you try to store this tensor as dense data, you realize very few people will buy a lot of products, so it's a very sparse, only few users, and if you write a review, you only get these few words. So actual data in this space is very, very sparse. On the other hand, if you try to represent it using a full dense data structure, in here, you don't even have enough space in an entire data center to store this tensor. It's huge. But the nice thing is if you don't store the zeros, and if you only store non-zero values, that data set will fit in my laptop. So because of that, it's very important in many of these data sets to use sparse representation to store them. And as data get larger and more complicated, sparsity is becoming more and more important. So one approach to doing sparsity is write libraries to do sparse computation. So if you look at out there are libraries, many libraries writing many sparse operations. So problem there is how many operations you are writing in the library because to get high performance code. So there are codes for linear algebra, there are codes that do data analytics functions, and even in physics doing quantum chromodynamics, and the list goes on. So this is not simple. Even the most important thing, which is the sparse matrix vector multiplication, that's probably the most commonly used sparse routine. written by many people, you think it should be easy. But if you look at multiple libraries, there are many implementations, because if you're just doing sparse matrix vector is one thing, but if you want to add another vector to it afterwards, so update a vector or something like that, to get the best performance, you need to write a very handcrafted library routine to do that. Otherwise, you will get suboptimal performance. In fact, if you look at OSCE, this simple routine has 282 different specialized variants, because they have to deal with different sizes of matrices and vectors, different shapes, different architectures. All these support just blows up. And this is just only about expression. One thing about sparsity is you can represent the sparse matrices using very different formats. So for example, if you have a thermal simulation, you might use the CSR format, or web matrix might be used the double CSR format because it's very sparse. Some of those things are inner blocks that might use block formats. Data analytics most of the time use coordinate formats, and this goes on and on and on. And there are even more different formats as you go into vectors and also go into more high dimensional tensors. And the problem with this kind of adding formats is now even the simple expressions now have the combinatorial blow up of having the right format. So writing these libraries is becoming harder and harder, and of course where you run the library also matters. So you can think of this as an untrackable problem or permanent employment for a large group of people who write this library code. So we want to change the landscape. Another way to look at this is, why do I try to write all these library codes? Why can't I write a bunch of binary operators and compose them like we do many of the software systems to build these complicated functions? So I will show you why this might not work. So this is a function called stdmm used in data analytics. And what this function normally does is do a dense matrix multiply using two dense matrices. And in here, I assume you are doing 8 by 3 matrix, so you're getting 64 inner products in here. And then you are going to do a component-wise multiplication using a sparse matrix. So assume you have a very fast matrix multiply, you can find that. And then you do that, and then you have another function, then do sparse matrix, dense matrix, component-wise multiply. Okay, how do you combine these two? That looks like a perfect solution. So if you want to calculate this value, of course you need to calculate this matrix multiplication. You do that, and you provide the value here. But if you want to calculate this value, you don't need to calculate this, because the problem is that value is 0. So if you do a matrix multiplication at the beginning, you're going to, in this case, calculate 64 inner products to just throw out 54 of them without using them. So doing this component-wise is not good, because you are doing way too many extra computation. Understanding the full computation and doing it together, I might be able to just basically limit my computation of inner products to only doing 10 and get asymptotic within this computation. So that's why just doing components is not good. You need to actually know the entire expression you are computing, so you don't go do extra computation. You don't waste computations. So what we are building is a system that you can give any tensor algebra expression in here, and any format for all the tensors and matrices and vectors we are doing in there. And we want to basically produce efficient code out of that. And that's what the Taco compiler is all about. And today I will go describe Taco compiler to you. So I'm going to talk about 4 things today. First, give you a little bit of a primer about sparse code and data. By the way, let me ask you a question. How many of you know something about sparse matrices and sparse representations? Okay, that's about half the room. But I will also go down a little bit describing some of those formats, so if you haven't seen sparse representations, you won't be lost. And then I will talk a little bit about code generation. How do you get code that runs very efficiently through these data structures? Don't do unnecessary computations, or don't visit unnecessary nodes in here. And then I will talk about format abstractions. I showed you there are many different formats to represent these tensors, and I will talk about how to deal with this complexity of formats and deal with that in a code generation environment. And finally, I will finish by evaluating our system. So let's start by looking at sparse code and data. So I have this 3 by 4 matrix, and there are a bunch of values that are 0 in this matrix. But what's the easiest way to represent that in memory? Easiest way to do that is basically line them in memory, because memory is one-dimensional, and then represent this as a simple one-dimensional array in my memory. This works perfectly well in most cases, and this has a lot of nice properties. For example, given a position in here, position 6, I want to find what the coordinates are. Simple. I know my in a block size that's 4, I can calculate the row and column coordinates directly out of that. So given a position, I can immediately calculate the coordinates. There's no issue with that. More importantly, given a coordinate, can I figure out where my data is? And that's very important, because I want to, that means I can random access to that memory. And basically this is very simple too. I have this very simple formula, I calculate and I get this value. But there's one problem in this format, because I have allocated storage for all my zeros. So if you have way more zeros than data, I am just wasting storage. And worst case, I will probably do computation on zeros, add zeros, multiply zeros, just waste of time. So the better way to do that is to compress this. Put them all together into one representation. Now, if I have this compressed representation, given a position, I want to find a coordinate. Can I? I have no information. I lost a lot of information. So at this point, additional set of data structures has to come about to represent my row and column position. So the first representation I talk about is in here is going to be the coordinate representation. In coordinate representation, what you have is for each value, you are representing the row and column coordinates. You can keep it as multiple arrays, or basically you can do pairwise in a single array. Depends on the representation. So you have this, you can do that. Now, going to position to coordinates is pretty easy. I know exact position. I look at that position in row array, I get the row location. I look at the column array, I get the column location. So this is great. This is a good representation. Except there's a little bit of extra data you store. So if you look at this thing, what you see is for rows, even though I don't have this many rows, I replicate the row value multiple times if there's a column data in here. So row value gets replicated many times. So there's even a better representation for doing that. It's It's called the compressed sparse row representation. So there what you have is, for each of the row, there's only one value per each row. It's not got replicated. And it says where the column starts for that row. So this row starts 0, row 1 in the column array starts at location 2, row 3 starts at location 5, and so on and so forth. And the range is basically from here to 1 minus that for that column. So this representation now, given the index I would go with a coordinate to position. I can easily index it because this is a one-to-one correspondent for my basically rows in here in the position array. And now I will say, now my columns are between 2 and 5. So now I can figure out in this representation that my columns are represented in this range in my column array. But now there's an interesting problem. Assume I want to find the second, third column in here. I can't do a direct access. Now I have to go through in this one, iterate over until I find that value 2 to get the second column, and that will basically give me that value. So I have to go through iterate over this thing. So this brings out. Okay, let me go the other direction too. So now if I want to go through from position that I know where the D is, I want to figure out the indices. Column is easy because I look at the same position in the column array. But now finding rows means I need to basically iterate over this until I find the range that belongs to. And then that gives me the value. So there's a little bit of a meta point in here. When you have data structures that don't have random array accesses, iterating over them is a little bit complicated. So if you want to iterate over data structures that doesn't have random access, what you have to do is there's probably a natural one order that you have to iterate over there. That order gives you the most optimal, the lowest cost iteration order. If you try to go on some other order, you will get asymptotically bad. You won't have order 1 going from one element to next. You will probably get order n, order log n, go from one element to x. So if you are iterating over n squared array, you might not get n squared number of accesses. You might have to do n squared log n or n cube number of accesses. So it's very critical that you iterate correctly on these data structures, and that put a lot of restrictions on what you can do with these data structures. Whereas if you have random access, you can go anywhere, so you can have any part. Sometimes it might not be the most efficient. So for example, cache efficiency might dictate certain iteration order, but at least asymptotically it gives you the same performance. So another interesting thing that we observed was these complicated tensors have very, very complicated representations. So assume they have these 3 tensor in here. And this can be viewed as this very complex data structure representing these tensor. But one observation is, even though there seem to be 4 different data structures and 5 if you consider the values in the structure in here, instead of thinking about this in one complex monolithic beast, one thing we can do is levelize it. So that means every level of the tensor, the matrix, we can say some data structure belongs to that level independent of what happened on the other levels. So to give you an example in here, this outer level in here is dense because all 3 in that space we are representing, 0, 1, 2. So it can be represented using these slices, and that's the only data that's necessary. Then the rows basically can be represented as something like a CSR relay data structure in here. And the columns can be represented using this one value for each column in this representation. And the nice thing is, these are independent. For each dimension, you can look at the representation, and if you look at that, what we call is the outermost is a dense representation. The second one is a compressed representation. This is something like one dimension of CSR. And the innermost is a singleton representation because there's only one value for that dimension given what comes from the previous dimension. And we can go do this representation. Nice thing about this kind of representations is these building blocks, per dimension level building format building blocks can be used to build a lot more complicated structures. So let's look at this 2D matrix in here. If we say outer dimension is dense, the next dimension is compressed, you can represent using this compressed representation. In fact, this is the CSR representation, if you get this representation. So you go level by level, you get this representation and you get CSR. If we do outer dimension compressing as given here, and inner dimension singleton represented for a level format in here, you end up, oops, what happened? Sorry. Sorry, okay. So you get coordinate representation in here. Okay? So we can just push this move forward. So what happens is now we have come up with 3 different level formats that represent levels. And now we can use these formats to build any tensor format. So I showed you how to do coordinates matrix and CSR using these 2 representations. But we can do more. So basically we can use that to represent most of the other representations that's out there for matrices and even high dimension tensors using these 3 formats. So we can break this thing apart in there. And furthermore, if we can add 3 additional different level representations, one for hash, one for a range, and one is just an offset representation. These details are in the paper that you can get. I'm not going to go too much in details in there. And at that point, I can basically build things like hash maps, dia format, block dia format, get all these representations built using this level format. So instead of getting really worried that we have this very complicated multiple data structures, what we have done is we have broken into multiple levels and very specific level formats, and then we build these higher dimensional tensors using each level format. and each level is independent what happens in the other levels. So this gives us the ability to kind of argue and basically do kind of recursive code generation and recursive understanding of the system. Next thing I want to look at is how to generate code. So assume I have this tensor multiplied by a vector, and this is in Einstein format, so there are two different free variables that produce the output in 2 dimensions, and there's this summation variable that gets summed up in here. And now we can represent this as output as a matrix, dense matrix, and the input as the 3 tensor, and this vector also dense. So I'm using this as this level formats in here. And to code for doing this pretty darn simple. So probably fresh college freshman, you should be able to write this. Very little bit different than a matrix vector multiplier, not that different. Now, I suddenly realized that some of these dimensions are sparse. This entire thing is just zeros. So can I get rid of that and make that sparse? So from here, I am using the word sparse to represent basically compressed representation. So I am using it interchangeably. So I apologize for that. But if you say sparse, you will see that. So now the dimensions will be sparse, dense dimension for this representation. And only thing I have to change is little bit in my code in here to get this code going. And I realized the next dimension also sparse. I represent it as sparse, and I have to change my code a little bit in that dimension of the code to do that, to get that. And then I want to look at also inner dimension and say, that's also sparse. I want to represent this using a compressed or sparse format, and that's the code I have to change. Now get things a little bit tricky. I realize that my vector is also sparse. Now I want to represent that also using a sparse representation. Now, in inner dimension, I actually basically doing this multiplication of 2 sparse data structures. This is a little bit of a tricky piece of code. So I will show you how to generate all these things. So I will do that. And if you think this is complicated, let's assume a little bit of a more complicated expression that I am going to add 2 different tensors before you multiply it by a vector. And to get the best performance out of that, that you're not going to do any extra computation, you have to end up generating or writing this piece of code. So this is why library writers have permanent employment, because they need to keep writing these kind of very complicated piece of code to get performance. And so, of course, we don't want to do this by hand. So this is why we come up with code generation. So what we are going to do in Taco is, given any expression, here the expression we just worked on, and given its tensor representation by levelized format in here, we want to generate the most efficient code in here. And we get the tensor expression, we get the format in here, and we want to generate the most efficiency code. And I'm going to talk about 2 different intermediate representations. The idea about this is we need to have right representation or right abstraction. So 2 different abstractions we worked out that help in here. One is called iteration graph intermediate representation. And then they are going to code generation, we have a representation called merged lattices. So these 2, if building together, has a very mechanical way of generating this very complicated piece of code. So let's go look at how to do this thing. So again, this expression in here. And if you look at this tensor, if it is dense, you can represent using a nice dense iteration space. So this is a rectilinear 3D strip iteration space. Even though the vector is a 1D, you can actually project it and expand it to 3 dimensions, basically, and that's how you can look at that. So there are 2 different data structures in here. To do the multiplication right, you have to co-iterate over both data structures. But these data structures are identical. The iteration space is identical. So merging these 2 iteration spaces together is no big deal. And then by doing that, you can actually do the computation of the output, which is also in the same iteration space. So this is why you can write the same loopness for basically iterating over B and C and A, and then you just basically write the right access function you are done. It's not the same in sparse. There are multiple things going on in sparse that you have to worry about. First of all, B is represented using a certain format that gives you a restriction on how you can iterate over B. What happened? Okay, sorry. thing about Keynote is you have to start from the beginning of each slide. So you need animation and everything. Okay. So what we have to do is, because it's representation, you have to first iterate over I dimension and then the j dimension and the k dimension. You can't go in the other order because other orders would be very expensive. So this gives you a restriction on how you can go through this data structure. And of course, k is one dimension, so there's only one to iterate over that. And then, the interesting thing is these are very different looking data structures. The non-zeros are not exactly the same. And then we have to co-iterate over both of them. And that basically says I have to iterate this k dimension on both B and C data structures together. And then the next thing is that we are doing a multiplication in here. That means I need to do an intersection of those two to produce the result. Because only there's a result if there's a value in that location for both B and C. So I do this multiplication. So this representation gives us the ability to think about how this computation has to be done. The nice thing about this, and also the output has to happen in these different dimensions in here. Output doesn't have to get co-iterated because it's for all iteration basically you're producing the output in here. And this representation, a very nice representation, that for this expression, what we found was any tensor algebra expression, we can write this iteration graph. And gives us a very mechanical way after you generate the iteration graph to go and generate code, which I will get to next. So even these complex expressions like multidimensional blocks per expression, multiple loops, indices in here, we can represent everything using this iteration graph that deal with all the input as well as the output. So now, how do you take one of these iteration graphs and co-generate code? So we can, again, this levelization concept comes into play. What you can do is you can look at a level. This level, there's only one input. So I can just iterate over that input. I don't have to do anything extra in here. This level, there's only one input coming in and assume that's sparse. And I write basically how to iterate over a single sparse dimension. Things get a little bit complicated in here because I have to merge two sparse dimensions. Both B and C are sparse and I have to generate in here sparse dimension. And then finally I have to generate the compute statement with the computation. So next, let's look at how to do this kind of merge dimension. So in a dimension you have two levelized formats that needs to be merged together. Assume both are sparse. How do you go about that? So to do that, let's look at two vectors. And these vectors I want to merge together. And what you can do is assume these two vectors are sparse in here. So it's represented using the sparse representation in here. And because it's doing a multiplication in here, what I need to do is I need to find the intersection of these two. In our merge lattice representation, intersection is basically represented in one node. And it says while both B and C has data, do the intersection, and if either one of them run out of data, I'm done. Because to have intersection, both has to have value in here. And now I can use this to generate code. My code basically says iterate over the loop. Hopefully you can read the text, it's somewhat small. Sorry about that. So iterate over this code in here. And let me go, and then basically insert if both B and C has the same value, compute here. So let me just iterate over that. So assume at the beginning I initialize both of those values in here. And then I look at until I run out of either of the data structures. And I calculate what's the smallest index in here. If the index is the same for both B and C, aha, I have to produce the data out here. I produce the data. And then I keep updating both indices in here. And I keep repeating this until I go and find another data item that basically has the same value and produce the output. And then I run out of values of this called C, I'm over with C. If I'm done with C, I'm done. That's all the output is. I produce the entire intersection. So intersections are simple. I go do this code generation here. However, unions are a little bit more complicated. So if you add in two things, I need to union the data structures in here. And basically, union has to be, this is my merge lattice, it's not that huge. What did I do? Okay, sorry. Unions is basically can't be done in a one lattice point. What we do is we extend union into intersection and leftovers. So the intersection is says if both A and B have value, you have to do the actual addition. Otherwise, you just have to copy the other value. What's the non-zero value? So you do that, and you build this lattice in here to do this computation. And then now code generation again can be very mechanical. So you have to generate code when both B and C are available, and you run this code until B and C are available. Now assume I run out of C, and then what do you have to do? Now you have to copy the rest of the B in here. So I have to generate this piece of code that copies the rest of the B. And in the case I ran out of C, I had to copy the values of C in here. And I generate that piece of code, copy the values of C. Now I have to go generate what's inside this code in here. Again, I go through my lattice in here and say, okay, look, if both B and C present, I have to actually do the addition. If only B is present, I just copy B to the output. If only C is present, I have to copy C into the output. So now I have a very simple mechanical way of generating code by working through this lattice. So first you have to construct the lattice, and generate code is basically simple walk through this lattice structure. And now assume I have a little bit of a complicated data structure like this. So I am doing B plus C times B. And this is my lattice. And then I basically keep visiting my lattice nodes and generate codes. It's a very mechanical process. Even if I get something a lot more complicated than adding three things, I just basically visit each lattice points in here and keep generating code. And then I got that very efficient piece of code that I showed before that does not iterate over, go over anything that doesn't exist. So I don't do any computation that's not necessary. And we can do even more optimization. Assume we know that D is dense. What does dense mean? Dense means that D is there for the entire range. So there's no value in A and B and C that there's no D value. So what that means is if you look at this lattice, there are a bunch of nodes that cannot be. Because you can't have a place where D finishes only, or case like that, D finishes early. So what we can do is we can get rid of these nodes, if you know that. And this is the only lattice left in here. And now when you iterate and generate code, we get again a very efficient piece of code that don't have this unnecessary conditionals or unnecessary loops in here. So we can even do further optimizations like that. And now what we have is, for given any expression, if they are represented using the sparse formats, we can generate the most efficient piece of code that basically guarantees it only iterates over data that actually corresponds to results. I don't do any computation in here that later I'm going to say, oops, I don't need it, I'm going to throw out. I'm only visiting the data, I'm only doing the computation that will end up in a result if this data value. So are we done? There are certain things that still doesn't handle, so I will tell you one example. So assume I am doing matrix multiply, basically. And assume all these are represented in row major order. So here's my iteration graph for the matrix multiply. So what this tells is I do a linear combination of rows of matrix multiply. So if it is dense, I generate no problem in here. Again, no problem in here, even though there's a merge, I can generate that because both are dense. And then if the last dimension is dense, no problem, I can generate this code, not an issue. Now the problem is if you have sparse dimensions in here. So if it is that, I can generate the sparse code here. Things get very dicey when you have sparse dimensions in here, with C and A as sparse. The problem in here is we have this reduction happening before we are updating. So what that means is we have to scatter a result into A multiple times. So you are iterating over the writing few things of A, the entire A, and then writing another few things in A. The thing about sparse data structures is you don't have random access. If you don't iterate from beginning to end one time, you go multiple times, very, very inefficient. So this inefficiency doesn't help you because then now I have to do this search through this structure to put few things in there, search one more time in here. And that can add basically asymptotic slowdown to my execution. So what do you do? So what we do is we have this reduction happening before we are updating. So what that means is we have this reduction happening before we are updating. So the problem in here is we have this reduction happening before we are updating. So what that means is we have this reduction happening before we are updating. So what we do? One simple thing to do is split this loop J into two different loops in here. And then, now when you work on one row in here, instead of writing into a sparse row, I keep a temporary structure called a workspace that's dense. So dense ones I can do random access. So I only blow up one dimension, one row, because this could be much larger than the sparse one, but it's only one row. I don't have to blow up the entire thing in here. And then I can update once I accumulate this. So what happens is now we accumulate in here into this multiple times, get accumulated this W array in here. And then once it's done, we copy the W array back to it. So by doing this, what we have done is made it possible to keep this intermediate data structure to do this and not have needed random access into my sparse array. So this one is nothing new. Gustafsson actually introduced this as optimization for matrix multiply a long time ago. But this is all handwritten code. So what we have done is formalize this thing and came up as a general mechanism, and what we found was this transformation helps in many other places. The MTT KRP optimization, even when you do a matrix add, if I copy it into workspace, it will reduce the amount of conditional codes you have to execute, conditions execute, because updating a dense array is don't need condition, you need random access. So I can do this in a very systematic way for multiple different systems. So now I'm going to change gears a little bit. So far I showed you is how to generate code when you have dense and sparse level representations to any expression, any complications. But at the beginning I said there are a lot more different representations, so how do we deal with that? So let's address that by looking at different matrix formats. So right now, if you look at code generation, we again showed you when you have multiple operations how to deal with that. And for each operation, we just right now only had each level there was only two different formats we could deal with here. But the problem here is there are many different data structures out here, and for each format. So now what you need to do is you need to have this combinatorial blow up again. As I showed in the previous slide, this is where we started, but there are a lot more different representations for these matrices, and you have to generate code. And of course, if you do a little bit more complicated computation, this again start blowing up in your face. So you can't write hard code this thing, and we need to come up with a much more systematic, programmatic way of doing this. And that's what I'm going to talk about next. So we looked at code generation to do in two stages. First, you figure out for each, this is for each level, what is the representation for all the operations. So here I am doing assume intersection or multiplication of two different vectors. And I come up with the higher level algorithm first. And once I come up with a high level algorithm, just understanding only the properties of these formats, not the format itself. There are certain properties of this format, say, okay, given these properties, I will with a high level algorithm. And then I will say, okay, now give me the runnable code given the exact format. So what this does, it show you how to compute for different data structures, and this is how to compute for multiple operations. So the idea there is we want to understand some high level structure to basically structure the code, and then for given specific format, we just need some basically almost a library function or small snippets of code you provide that we inline into our large algorithm, and we get our performance code. So let's figure out what options do I have. So assume I want to do an element-wise multiple of these matrices. And in order to do that, I need to actually do element-wise multiplication of two different vectors. These are two sparse vectors. So we have two algorithms. One is the kind of algorithm we showed before, which is a two-finger merge. You go through both structures, basically skipping over non-zeros until you find the matches in here. This is the kind of code generation I showed you before in here. But assume if you have an ability to do random access into C without expression. So at that point, I can just move over B And as soon as you find a non-zero, you just random access into C and see if there's a value there. If you use, I can just load the value. If it is 0, just skip over that. So I can do random access if random access to C is available in this data structure. So given these different level formats, it depends. Dense has random access available. Other formats don't have random access available. So for them, I can't do random access. Luckily, everybody has some way of iterating over that for representation. So we use that. So what happens is now I am doing element-wise multiplication of B and C. Assume these vectors are represented using one is compressed and one is hashed. And you suddenly realize hashed has random access. So what you can say is iterate over B because this only there you do random access. And for every time you find a value in B, do random access to C and get that. And if you actually do a compress and dense, you can exactly do the same thing because dense has random access. But if both are compressed, I can't do that. At that point, I have to simultaneously iterate over both data structures and do a two-finger merge. And by just looking at the properties of our this levelized format, I can come up with the algorithm we have to do. Now, what each levelized format has to do is, if we say as a property saying I have access to that, you better give you something. I say, okay, if you say you can do it, tell me how. So you can almost give a code snippet saying, okay, if you want to random access in a dense, it's easy. I can calculate the random access in here. In that. Hash, little bit more complicated, do the random access. I had to do a hash key calculation, go through the buckets and find the value. I can give you those. And for iteration, everybody says they can iterate over the entire space, and you have to provide some code how to iterate over this, and basically both calculate the position and the coordinate. So I get these codes in. So I get these codes in. These are almost like library code snippets, but they are snippets because instead of just calling big libraries, we need to ingrain them into our algorithm. So here's what happened. So assume I have this compress and hash computation here. So what we have to do is basically say for every element B, we iterate over B, find the corresponding thing in C. So what we have to do is for every element B, now say, okay, in compress format, tell me how to do this. I basically insert that piece of code out of that. And say, now I need to find this corresponding element C in C. Then you go to the hash representation and say, give me that. And voila, I can do that and include that. And then now I have this full part. Note that my overall algorithm didn't have to know about these code snippets. You only had to know about what features and properties are available for this levelized format. We do that because it makes it possible for you to add additional levelized formats. You don't have to change too much of the compiler. You need to tell its properties of this format and then provide us the code snippets that we can inline. So this can get more complicated. Assume now I am adding three tensors to produce another 3 tensors. Okay? And now I have to go level by level, figuring out all the complexities of the code generation in here, and then figure out the right algorithm to use, and then ask that level format how to do that. So some of these levels could be sparse, some of them could be dense, it depends, and it depends on the algorithm. So the code that gets produced is very complicated, something like this. And one thing I want to observe is there are colors for each dimension in here of each matrix, and there's a kind of color corresponding to how did I iterate over that dimension. So what that means is this is a very fine-grained combination of many different level formats from these what we got from level format. It's not like some kind of library code that you call out. It has to be integrated into this one function to get us the best performance in here. And what this gives us is a really interesting ability, because most of the time when you look at this functional abstraction, library abstraction, you just assume there's a cost in here. Every time you do abstraction, there's abstraction penalty. What we have done is move the abstraction to the meta level. The abstraction is at the compiler level. But the generated code is the most spaghetti integrated code you could see that people write by hand. But the nice thing is still at the compiler level you have some very high level abstractions. So you can think, reason, argue, produce code at that level, still viewing it as a very abstract system. But you don't pay any overhead because the generated code is this crazy spaghetti that basically otherwise run by hand. So this way, here's a way you can actually have the cake and eat it too. You can have this nice high level abstractions, but you don't have to pay the penalty, the abstraction penalty. Nobody you have to pay when you have this complicated abstractions because we are doing it in a compiler. So let's look at how well we can do it. Let's go and evaluate this system and see how we are doing that. So as we said, we can generate code for any expression. Give me expression, I will generate code. Of course, the problem is I don't know how good it is. It's hard to evaluate. So only way we can evaluate is there are, as I said, there are a bunch of library writers who wrote many libraries for certain functions, and we can go look at how we do that function. So there's no function that is very well optimized than sparse matrix vector multiply. If you do a sparse matrix library, if you don't do that, don't do anything because this is the most useful thing. That is what everybody uses. But in Taco, we don't do anything special for this. It's just another function that we generate code for. And so what I'm showing here is 6 different matrices out of Florida's sparse matrix collection. And I'm showing normalized execution time for Taco, and lower the bar is better. So there's all these basic library systems have code for sparse matrix vector multiply. The best one is probably MKL because Intel has I don't know how many engineers really focusing on handwriting these libraries. And what we are showing here is the sequential code. We are more or less in first certain cases they are a little bit better, certain cases we are a little bit better, we are competing okay. Then when you parallelize this code, it's very only MKL and we are right now producing parallel code for these. And there we are again going head to head with this very well hand optimized piece of code. We are getting basically exact same performance. So this is great news. The next thing I want to show you is that the code I started at the beginning, the STDMM code. So it's an important piece of code for data analytics. So IBM realized that, and they wrote a specific hand optimized function that do the entire this operation together. And by doing that, they get really good performance. On the other hand, if you use UBLAS, what you have to do is you have to find the best matrix multiply, dense matrix multiply. You have very good BLAST libraries to do that, you get that. And then use another function to basically do the sparse matrix dense vector element wise multiply. What you see is you get asymptotic reverse behavior because the matrix multiply, even though might be very efficient, you're throwing away most of the work in the final result. So by doing this, you're not getting good performance. You don't want to do that. You want to do the entire operation together. And we generate that code. Same thing goes for MDT KRP. This is a very important kernel in tensor factorization. And the Splat system basically do a lot of tensor factorization, has a handwritten kernel that do this computation explicitly. And they get good performance. On the other hand, matrix tensor tool blocks basically have to accumulate a bunch of different individual functions to do that. Again, they are off in computation for doing that. So generating specific code for the full expression when there's sparsity is very important. Not just it will give better cache performance and stuff like that, but more than that, it actually gets asymptotically better performance because you don't do certain computation when we know it's not used later because it gets multiplied by a 0 or in later. So you can drop those things. It gives you much better advantage. So the next thing I want to look at is, we said we can do a lot of different formats. So here's Taco, and here are many other frameworks out there to do sparse matrix computation. And there are many published formats to represent matrices, and tensors, and vectors. And if you look at all these other systems, they will work on certain set of formats. That means some poor souls spend their lifetime writing these individual pieces of code optimizing these things. And something like sci-fi has a lot of formats in here. Compared to that, Tahoe has a lot more formats in here, and we know we can add 2 more level formats and get a few more. And there's only 2 different formats that's published out there that doesn't fit into our model. And we find this is very nice. And also we have a very easy way of adding levelized format. So if you come up with a new format, assume you are doing GPU generation, you find a format that you think will get really good GPU performance. Adding it to our system is not that difficult. We give that ability, like if you realize cache alignment give you good performance, you can come up with a new format that has cache aligned, and we can basically add it to our system, and it will work with every other format because we have a way to combine everything together. So let me give you some more performance. Basically, again, sparse matrix vector multiplication. So here's a little bit of eye chart. So what I'm showing in here is coordinate format, representation of the matrix in here, sparse matrix using coordinate format. And I'm showing the results for coordinate format for a bunch of different matrices represented in here. And then I'm showing results for Taco as well as a bunch of other frameworks in here. And if you look at each row, the fastest one get a 1. And everything else is how much off from that. So for example, if you look at the first row, everybody except MTL4 get the same performance. MTL4 was 1% slower. Last row says, if you use a web-based matrix, Taco and Sci-Fi got the fastest, MKL was 2% slow, but MTL4 was 64% slow for that computation. And TensorFlow didn't implement this format, so we don't have results for TensorFlow. We can go look at other formats. So the next format we can look at is, when we have coordinate, there are 2 ways to represent coordinate. One is structure of arrays, that means each coordinate is its own array, or array of structures where each coordinate is represented as a pair in here. So if you do that, basically the only other representation who uses it is basically TensorFlow. And we of course can generate it. And we basically are much better than TensorFlow. We are running basically at worst, we are 17% better than TensorFlow. In best, we are like 2.2x faster than TensorFlow because we are generating much faster code. And then most probably used format is probably CSR. And in here, MKL library that probably is bunch of poor souls had optimized for a long time actually does very well. We are not that bad. The worst case we are about 23% slower, and in few cases we have about 3 cases we are beating MKL by few percentages. So completely. And then if you go to a format like diagonal format, their MKL does really well. We are comparable with Sci-Fi. What we found, of course, MKL doesn't have source code, so we had to kind of info what they're doing. MKL does a couple of additional optimizations like blocking or tiling that we are not doing right now. So it looks like MKL has additional things that we want to do in the future, and they get better performance. And then finally, L format basically is only implemented using MTL4 system, and then they are good in everything except for this one benchmark that we are doing better. So what it says is, even for something like sparse matrix vector multiplication, we can support everybody, and we are not that far off in our first system. This haven't been completely fully tuned. There are a lot more things we can do to basically match everything because it's a compiled generation. Next question I have is, if you are doing sparse matrix vector multiply, how do you represent the matrix in here? So in our levelized format, you can basically have 2 levels. Basically, I'm only looking at 2 representatives: dense, sparse, dense, sparse representation. If the matrix looks like this, it's very close to dense. Dense basically win. The normalized time, the best shorter bar is better. Dense win at this point. However, if you get to a thermal matrix that has a lot of this kind of diagonal type patterns, dense sparse gives the best performance. Sparse is basically DCSR. Dense sparse is basically CSR. DCSR is sparse gets pretty close performance. But if you have a row slice matrix, sparse dense actually give you much better performance. And the same way, if you have a hyper sparse matrix in here, sparse gives you the best performance. So even if everything is constant, the shape of the data gives you different performance. And if you have a block sparse representation, for example, if you do something like a finite element, the inner, when you have non-zero, you don't have one non-zero. You might, if it is three-dimensional, you might have a 9 non-zero 3 by 3 blocks in here. So you can think about this as a just normal matrix representation, or you can think about it as a 4 tensor. The inner 2 dimensions are the probably 3 by 3 dimension or 4 by 4 dimensions in here. They are dense dimensions. And the outer is whatever the blocks are formatted in here. And the nice thing is now when you code generate the inner things means they are dense, I can vectorize. Because I know it's dense, 3 by 3, I can get much better performance by vectorizing the inner dimension. And I get good performance by doing that, dense representation. So here's another way looking at when you look at some additional representation, coordinate, CSR and dia format. For certain matrices, basically CSR, by the way, is this, I have a question, this is speed up or runtime? Speed up, is it? No, it's runtime, it's runtime, so, okay, sorry, I couldn't get this, I just copied the slide today morning from my student. So, this is runtime, normalized runtime. So what that means is, a couple of matrices, dia format, when it's diagonal, actually wins. If it is not diagonal, if you represent something in a dia format, it's really bad because you have a lot of diagonals with a lot of zeros and you get really, really bad performance. So it depends. So if it is actually real diagonal, you can give a good win in here. So here's an interesting thing. In many cases, if you look at coordinate and CSR format, CSR wins because coordinate you need to keep some additional data in here. Basically, the outer dimension is longer than necessary. But in many systems, the data is stored as a coordinate in this, or at rest you get data as coordinate. So if you actually add the transformation cost from coordinate to CSR, just doing the computation coordinate might be faster because coordinate to CSR transformation is actually expensive. So even though the operation itself might be faster, what we do around it might make it not efficient to do. So it's very important to figure these things out. Next thing is, I'm again doing sparse matrix, sparse vector multiply. And both sparse matrix and sparse vectors have different densities in here. And if you look at performance, what you see here is, it again depends. Depending on the density. In certain densities, either dense vector representation is better. In certain, a hash map representation for vector is better. In certain densities, sparse representation for vector is better. So what that means is if you want to get really good performance, there's no one solution. You have to have all these different things. It depends on the computation you do. It depends on the sizes of each of the tensors and matrices. It depends on the shapes of the tensors and matrices. It depends on the sparsity of the tensors and matrices. All these will lead to different performances. So what we have is we have implemented this and we are releasing it in 2 different systems, and we have a current system that doesn't support all the different sparse formats, and within next month Fred tells me that we have the representation with all the sparse formats will be released. And so in the library representation you can basically tell what your tensors and matrices are represented by using combination of level formats. Then you can actually either load it or declare those data structures. And then you can just basically using operator overloading describe your computation, what you want to perform. And then you can say compile. Compile means it finds this expression in here. Oops. What did I do? Compile means it finds this expression in here, generates C closed, or now we are trying to generate LLVM in here, and then you basically compile it, create a dynamic link library, linked it, and then assemble means you know B and C, and tell me exactly where the non-zero elements are. It will assemble the matrix, and then compute means actually you run it. The other way to do that is we have this online system in here, where if you are just a scientist, you want to get something done, you can go to this website and say, aha, this is my computation. Please give me the most optimal piece of code. So instead of going to library and calling a library for the function, I can go to this place in there, write your expression in there, and then select the different sparsity factors in here, and we have some expressions that we have already generated in here, and then we can generate code for that. And then as I show you, I can basically go and try any expression you want in here, and say generate code, and it will generate the code for you. And so by doing that, you can assume if your scientists want to do something, you can go generate your expression, generate your formats that each data structures come in, cut and paste it into your library, and you're done. Finally, I want to talk a little bit about the future directions. So we right now have a system working on multi-cores in there. We are working with NVIDIA to generate code for GPUs. And also we want to generate code for distributed systems, and we are working with some standard folks to basically look at how to generate code for distributed systems. Of course, these days you can't do any research project unless you do something with neural networks. And luckily for us, a lot of neural networks have nice sparsity patterns, and so we are looking into how we can use this to basically get this good performance for deep neural networks that has a lot of sparsity. Something we realized, and a lot of other people realized, is even though you have tensor algebra, there are many other interesting operations that can be viewed in this framework, that when the operations, instead of doing plus and multiplication, perform other types of semi-rings. So things like softmax functions and sigmoid functions can be implemented using the same framework. So we are looking into expanding this into additional semi-rings. So instead of doing sparse matrices, if you're actually using dense matrix operations, so for example, if you look at systems like Halide that do dense operations, to get good performance, you have to do a lot of other transformations like tiling and loop reordering and stuff like that. And one thing we also realize is, even though we do kind of optimal code generation for sparse, a lot of computations or a lot of data might be mix of sparse and dense. To get good performance, you might have to do things like tiling and other transformations. And so we want to expand that, add into this system, and again expand this as a language, like some schedule language like Halide. Finally, it's nice to have a scheduling language and also way to specify these formats. But can we do some of these things automated? So all these things are mechanisms to do, but can you do a policy? Given some large computation, can we come up with the formats and write transformation? This is not easy, because something like Halide, the only dynamic thing you have to know is the data sizes. Most of the expressions you know at compile time, if you give the data size, I can say, aha, I think I can know how to generate code. But in basically sparse matrices, the shape of the matrix is not known until runtime. Shape can change. You can have diagonal patterns, different sparsities. So how do you figure out what's right? It can be a lot more complicated. You might have to do some sampling. Because if you look at the entire matrix, you might do too much computation to figure out what's going on. So some kind of sampling or some inspect executor can all go together to do something. So there's a lot of interesting work that we think can be done on top of this system to make it useful. So finally, we have more information coming on at UPSLA. For example, there will be talk on format abstraction on Wednesday. So I gave you a little bit of a snippet on that. If you want to know more, you can go to the talk, and probably Stephen will do a much better job describing, because he did all the implementation, so he knows the details in and out. And then at the beginning of the talk, I promised that I'm going to talk about graphs, which I didn't. And if you're here to know about graphs, we also have another talk on GraphIt that basically will cover how our DSL for graphs. And with that, let me stop and take any questions.
Yeah, I was wondering, how well do those sneak that you show or work on SIMD architectures?
Oh, something like GPUs kind of thing?
Yeah, for example, GPUs.
So we actually are working right now with NVIDIA, GPU code generation in here. They have a bunch of libraries that they have done things by hand, and there are issues, interesting issues, things like scheduling, load balancing. So we are looking into interesting patterns and how to do that. So hopefully within the next few months we might have some solutions out there. So we're just about to get into that.
Mm-hmm.
The nice thing is we understand the patterns in here. We can generate code, and even more importantly, so for example, if you know some kind of CND block size, I might be able to play with my format and say, aha, I will give you a format that will be a lot more efficient for that. Like for example, if I have a format of inner block size of 4, dense block size of 4, I can basically symbolize that much better. So I might be able to play with both formats and code generation to actually get good performance in this. So we are playing with all these constraints.
Yeah, one problem I was thinking of specifically is if you want to do some kind of vector load and your data is sparse, that might not work properly.
So actually it's interesting. Contrasting with graphs, if you look at graphs, all the loads are crazy. They go all over memory. There's no locality or whatever. So the entire thing the architects built in last 20 years is just useless. So we can't, no prefetchers, no anything, no cache scale. Here, on the other hand, it's very interesting because all the data is loaded in a regular streaming pattern from memory. So you're going, even though it's sparse, I'm looking at it in its order in here. So ARMCO basically is good. What's interesting is INCO. INCO is interesting. This is a little going beyond INCO. There's a lot of operations that, like, for example, two-finger merge is a bunch of branches that always goes in the wrong direction. Branch prediction doesn't work, but we know what's going on. We are merging two things. So instead of just issuing branches, can we do something better in hardware than do branch prediction? And the other interesting thing is, I know where the output goes, but the next output goes depend on where the previous non-zeros were. And if you do it normally, it's a very sequential dependence. I don't know where the output goes, but I kind of know some higher level information. Can I use this in hardware to do something better? So there are opportunities in hardware, I think, to do some stuff better. And we are also working with NVIDIA, looking at what are the interesting primitives that we can do some of these computations faster.
Thank you.
Can you tell us a little bit more about how different sparse representation formats are suitable for parallelization?
So something like this is for input. If the output is dense, input it's a loop parallelization, and then it becomes a load balancing issue. Because something what might happen is there might be certain regions how we partition become load balancing. So for example, do you partition logically? So that means you take the iteration space, you partition logically or physically. Logical is easy to line up because it's logical partition match between the two different data structures. If you partition physically, basically you actually get the load balance partition. Each partition has the same amount, but now it doesn't match up because this might go from 0 to 8, this might go from 0 to 26. And it gets imbalances in it. So that gives you some interesting load balancing questions. And then things like cache alignment. So if your output is in there, so part of that is we don't have the perfect answers, but between new formats and code generation, I think we can do a lot of interesting innovative things. We are just getting there. I mean, the simple things like producing dense outputs using any combination, I think we have good solutions right now. But more and more complicated formats, parallelization is going to be interesting. And this is something we are right now studying. It's a very good question. And what will give us is, the problem right now is formats are so expensive to do a new format, because when you come up with a new format, you have to rewrite all the libraries. People are stuck with the existing format. We, on the other hand, because we can generate these things, we have a lot more flexibility to change format, change the intermediate formats, do a lot of these crazy things. And I think that gives us a lot more opportunity to do things like realignment and all these things. So we are trying to figure out how we can benefit from this, our malleability of the things. So I think this is open question. If anybody want to work on it, I mean, we are going to make this thing open available, and I think I have a feeling that there could be many different format changes and also code generation changes that can give performance things like Cindy, parallelization, distribution, all these things. I think the current representation doesn't seem to be the best match in some of these things. But if you make it easy to rapidly find different representations, I can be able to come up with this analysis.
Right. All right, I think we can thank someone once again, and maybe before we do that, it's nice to give a gift to your keynote speakers, and we thought, well, we're in Boston, and Saman is from Boston, so the typical idea of giving someone a local themed gift, it makes sense for a guy from Minnesota to do, and David from New Zealand for SLE. So we brought gifts themed from our own region. So this is a gift from Minnesota.
Thank you. I thought this was some oranges, but it's not oranges.
So there's a little Minnesota apple brandy. There's some Minnesota maple syrup and a Minnesota pancake mix. So you can use the syrup in a cocktail with the brandy or on the pancakes. So however you like to do that. So let's thank Saman once again for a wonderful.